Let's talk about counting. These counting techniques can be used to solve a lot of discrete probability problems. I will be presenting factorials, combinations, permutations, and triangular numbers in this short presentation. And I will try to give you some visual proofs of the formulas that give you the number of permutations, combinations, or triangular numbers, or the number of points in a triangle. So let's take a look at factorials first. Here I have 5 objects. They are just shapes here, or the letters A, B, C, D, and E. Order matters when you're looking at factorials. We are trying to count the number of ways to arrange these 5 objects in a particular order. So I've got them in a particular order right now: diamond, circle, rhombus, equilateral triangle, right triangle. And if I reorder them, I have a different order. That's a different object I want to count. For the next slide, we're just going to use A, B, C, D, and E because it's a little easier than looking at all these shapes. Take a look at this. Here I found something on the internet that would generate all the combinations of A, B, C, D, and E in every order. So this is 120 copies of A, B, C, D, E in 120 different orders. So this is A, B, C, D, and E in every order possible. There's 120 of them. We do not want to count by hand when we are looking at the number of arrangements of some set of objects. So what's a formula that we can use to make this easier? Take a look at this. I've got 5 slots, 5 letters. There are 5 possibilities for which letter goes into the first spot. So I'll choose one. Now I have 4 slots and 4 letters left. 4 possibilities for letters that go into that slot. So I'll choose one. 3 possibilities. Oops. So I'll choose one. 2 possibilities. And then last, only 1 possible letter for this slot. So how many arrangements could I have made there? Well, 5 times 4 times 3 times 2 times 1. That's what we call 5 factorial. 5 times all the integers smaller than it, not including 0 or any negative numbers. That gave us an idea of how to compute all the possible orders of 5 objects. We just want maybe to pick a subset of those, maybe 3 items in order from 5 items. But our order does matter here. So as you can see, I can just start with the list of 120 arrangements of 5 items, but I can just throw away the last 2. But I've got some redundance here. I've got ABC twice, ABD twice, ABE twice. Why twice? Because for every set of 2 that I throw away, there's 2 orders, ED and DE, CE and EC. So we need to divide 5 factorial, our total number of arrangements of 5 items, by 2 factorial to get only these ABC, ABD, ABE. And this is how we get the number of arrangements of 3 items chosen from 5. In general, the formula for that is n factorial divided by n minus k factorial. And what you should think about is that you are throwing away n minus k items, and you need to divide out by their order, because their order in the trash does not matter. Last, combinations. maybe we're just grabbing 3 items out of 5 and we don't care about their order. Once again, I started this list of 120 arrangements of 5 items, but I didn't want to put it all there. We're throwing away 2 items. We know we need to divide out by 2 factorial. But notice this, CBA, BAC, ABC. If we don't care about the order of the 3 items that we're choosing, then we have 6 choices for how they're ordered. And we need to divide out by that, the number of ways that our 3 items can be ordered. In general, this is called a combination. We're choosing 3 items from 5 in our example. And in general, we can say that we're choosing k items out of n items, and we don't care about order. So we're dividing by the orders of the things we throw away, and we're dividing by the order of the things we keep. Think about this. It turns out that n choose k is equal to n choose n minus k. There's a nice symmetry here. After all, if we don't care about the order of either the things we're keeping or the things we're throwing out, we can easily switch the roles of these 2 parts and we'll have the same thing. Last, triangular numbers. Triangular numbers are called triangular numbers because they are arrangements of dots in a triangle. Alright, let me show you what this means in a more mathematical notation. I've colored it now so that you can see that we've got 1 dot here, 1 plus 2 dots here, 1 plus 2 plus 3 dots here, 1 plus 2 plus 3 plus 4, and so on. In fact, we can write that using summation notation as the sum of the integers I from 1 through n for a triangle with n on each side. But we don't want to do this addition by hand. That is annoying and time consuming. So how can we mathematize this to make it a little bit easier? Let me take my triangle. I've sort of skewed it a little bit here to look like a right triangle now. And I'm just going to duplicate everything in it and then move those dots and flip them around. Notice that that looks like a rectangle. And how many on each side? N plus 1, n, pardon my handwriting. And this gives us a really nice formula. We all know the formula for the area of a rectangle. And since our original triangles made it up, it's just n times n plus 1 over 2. If you can remember this visual proof, you'll never have to remember whether that's a plus or a minus, which is one of the common mistakes when using these summations of integers. Good luck!